Awesome. So the first thing that I want to quickly talk about is just, I guess maybe not everyone might have a question, like an idea of like what are the things that maybe macroeconomists deal with, and I'm not going to really go through macro models, but I kind of want to talk about, and I hope some people will find this maybe like not good enough, but it's just like a high level overview of talking about like what are the specific computational problems that macroeconomists deal with, and in particular, those problems that macroeconomists deal with are problems which optimization people would call variational inequalities. So variational inequalities are mathematical problems which consist of two objects, namely a constraint set X and an optimality operator called F, which takes you from of constraint variables X to some high dimensional space Rn. And so here I'm assuming that like the optimality operator is a function from X to Rn. More generally, this can be also a correspondence, a set value mapping, which is going to give you a set of optimality conditions. And this object's variational inequality defines an optimization problem, which is known as a strong solution of a variational inequality. And effectively, what this solution is, it's a stationary point of this flow that goes through a constraint set and defines a set of solutions. So why am I bringing this up? It's because a lot of the problems that macroeconomists deal with, please confirm, deny, or just like criticize me on any of this. A lot of the problems that macroeconomists deal with are effectively variational inequality problems that a lot of people in the OR community have really studied, especially Tyrell Rockefeller and co-authors starting in the 50s have studied, where effectively you have a bunch of these models, and these models are characterized by some optimality conditions, and then you set these optimality conditions over your constraint set, and then you try to solve for these solutions. And these solutions really, what they are is they're strong solutions of some variation inequality. This is how we can think of them. There's a large literature on the existence of solutions for variation inequality. So these solutions are these conditions, there's a wide variety of them. So one common condition is for the optimality operator to be continuous, and for the set of constraints to be non-empty, compact, and convex. In the case where your optimality operator is set valued, then you would just relax the condition on your optimality operator to be upper and continuous. And just you would use kind of something like Cactan's fixed point theorem to prove existence. So it's very standard on how it works. But this is kind of like a very general framework of how to think about really, I think, any of these computational methods in macroeconomics. There's going to be some like other methods that a bunch of other methods that people are going to talk about on how to solve macro models. But you can think of all of these problems as effectively solving, in some sense, a variation inequality. So I think this is kind of like a really helpful mathematical framework to think about things, and the literature on this is like so well documented that it's like whether if you have a value-based method to solve these dynamic models, or a gradient-based model, or a policy-based model, you can all of these fit into some part of the literature of the variation inequality framework. So let's maybe go through some of the going backwards. Interesting. So let's go maybe quickly through some of the examples of variation inequality problems that you would be dealing with that are relevant to macroeconomics and that can be models of variation inequalities. So and actually before I go through that, I'm going to the slide is I want to quickly talk about how do we solve variation inequality if I have a variation inequality. The classic method to solve a variation inequality is the projection method. The projection method really dates back all the way back to the late 1800s, the work of Cauchy, who really introduced gradient descent. But it's really the first canonical method to solve the variation inequality problem. And what we're doing is effectively we're taking the optimality operator F, and then we're taking an opposite step in the negative direction, a step in the opposite direction of the optimality condition given by our mapping. And under certain conditions, we know that this particular method, the projection method, is guaranteed to converge to a solution of the variational inequality, the strong solution. And in particular, that condition is known as the monotonicity condition. So this is this bottom part here that you're seeing. And what, in some sense, this says is just that everything goes towards your solution. So whenever you're taking a step from one other side of your constraint set that is not necessarily optimal solution to another part of your solution that's towards your set of solutions, then you will be getting then you'll be getting closer to your set of solutions from all angles of possibles from your set of from all dimensions of your set of optimality conditions. So this result, by the way, is due to Nemborovsky, this particular non-asymptotic convergence result, but the really initial results that were asymptotic convergence results date back to like the mid-50s. And there's a bunch of other results. So like if, you know, especially in this community, like where we're thinking a lot more about computational methods to solve these problems, there's been so much work done, for instance, on extra gradient methods or optimistic gradient methods to solve variational inequalities that have been shown to be more efficient, more effective at solving these problems, or more stable, because a lot of the time we're dealing with instability issues. So there's a lot of literature there. There's so much to look at. Just something to think about for people who might not be familiar with this. Okay, so just go through a list of examples, and people are going to go through more and more complicated models. So it's just like to give you a high-level overview of like the things that we can model variational inequalities. So the first one, the canonical one, is convex optimization. You know, we're trying to minimize the function f over a set of constraints x. X here is assumed to be non-empty, compact, and convex, and f is assumed to be continuous and convex. And so in this particular case, you know, a minimizer, the first order necessary and sufficient conditions in convex optimization for a minimizer x star is given by this condition that, you know, if I take a step from this minimizer, a first order linearized step from my minimizer to any other point in my constraint set, the value of my function would be increasing. That's what this condition is saying. Can I point to this here? Oh, wow, that's crazy. Okay, cool. Yeah. So in this particular example, you know, clearly we have the same condition that we had before. Okay, never mind. We have the same condition as we had before here, right? This first order optimality condition. The only difference here is that the capital F is just given by our gradient function for our objective function, right? So in this setting, how do we then just set this convex optimization problem as a variational inequality? We take our constraint set. Okay. We take our constraint set to be capital X here for our variational inequality, and then we take our optimality operator to be the gradient of F. So what do we do here? We just because we're in a convex setting, you know, it's the necessary and sufficient conditions for our minimizer are given exactly by our gradient, so we can just set the optimization problem as a variational inequality problem. In settings where, just as a side note, where we don't have a convex optimization problem, which is going to be the case in certain of these macro models, you know, we're going to be dealing with much harder problems, especially in continuous space. The problems might become non-convex. Then this particular variational inequality solutions are going to coincide with local solutions. So in the case of f being, in our case, not a convex function, but any function, this first order condition that we have would be just a first order sufficient condition for a local minimum. And so in that case, you can think of also the variational inequality just representing to us some local solutions. So that can be becoming really useful, for instance, in macro models where we have non-convexity issues and we're looking for alternative solution concepts that would be dealing with these non-convexities. Awesome. Okay, so another example, the canonical one, is min-max optimization. In min-max optimization, we have an objective function. We're trying to minimize on one direction x and maximizing on another. There, the solution is a saddle point. And here we're going to set our optimality operator to be the gradient of x, the gradient of f with respect to x, and the gradient of f with respect to y negated this time around because we're maximizing on the other direction. And here, if we run the projection method on this variational inequality that we're setting, this particular algorithm is known as gradient descent. So this has been also very well studied, and computer scientists lately have been devising a lot more sophisticated rates of convergence, and they've gone through effectively this equivalence via variational inequalities. Okay, another example from economics is the error exchange economy model. So in that setting, I have a set of n consumers. Each of these consumers have an endowment of m goods. This is a vector in Rm, and they have a utility function which notes the preferences of our goods. The demand of each consumer, the demand correspondence here, just think of it as singleton value just for simplicity. The demand correspondence or in this case, function if it's singled invalid, is just the set of goods that maximize the consumer's Marshallian. This is the Marshallian demand of the consumers. So it's the set of goods that maximize the consumer's utility, given the prices that are inputted at the budgets that are determined by those prices, which is the endowment of the consumers multiplied by their prices. We have our excess demand, which is just the sum of the demand across all the consumers, and subtracted by the sum of the endowments across all the consumers. And in this case, the solution to the exchange economy is given as a competitive equilibrium, which are prices in the unit simplex. So we're normalizing all the prices, and we're looking for a price vector, which effectively will clear the market. So what are those two conditions? There, Walras's law holds, and then that all the goods are, the allocation of goods are feasible. And so this particular way of setting that, we can set that particular condition, Walras's law of feasibility, turns out exactly as this condition. What does that look like? Once again, it looks like a condition for variational equality. So I can now set the problem as a variational equality problem. And now if I run the projection method actually on this particular variational equality, this is going to be equivalent to solving the market via Tétonnement, which dates back to what year, 1854? Okay, another one, okay, games. So probably most of us familiar with games. You have N players. All players take an action. Once they've taken their actions, the environment broadcasts back to them a payout based on some payout function. This canonical solution concept is Nash equilibrium. We can do this for any other solution concept too, correlated, cross correlated, whatever you prefer. And so it's, what is this? It's an action at which no player has an incentive to deviate to another action, so they maximize their payout, fixing the actions of the other players. Once again, we can put this also as a variational equality problem, where the set of Nash equilibria of variational equality are going to be given, the set of Nash equilibria of the game are going to be given as solution to the variational equalities. What is this optimality operator? It's, I take the payoff function of each player, take the gradient of the payoffs with respect to each player's action, and then I take the negation of that particular operator, which we call the game operator. And in this case, now if I run the projection method, what I have is the online gradient descent dynamics, which computer science scientists have studied a lot in the last, I don't know what, 50 years. Okay, awesome. So an example of it actually before a game. So then what is it now? We're getting to the computational macroeconomic model, or the computational dynamics problems, right? So the really simplest dynamic problem that we have is a Markov decision process. So I have an agent or a player which takes an action at each time step. They encounter some, at each time they encounter some state. At that state, they take their action. Once they've taken their action, they end up in a new state based on their current state and their action they've taken at that state. And the way that they determine this action is via a policy which maps from your state to action. Once again here, we can think of this as an optimization problem. We can set it as a variational inequality. Using the projection method on this is going to be equal to policy gradient method. We can do this more generally for n player Markov decision processes. We can do the same thing, and then it turns out we're also going to get everything as a variational inequality. Now we can also run projection method on this. We're going to get the policy gradient dynamics, which have been also studied very intensely. And I think that's all of it. Okay. And so the main point that I'm trying to make is that, you know, there's the way to think about any of these problems, in my opinion, in macro is really as a variational inequality problem. And, you know, it's like different flavors of this. You might want to solve your variational equality because you might face different problems for each of these problems. So for instance, when you set the, you know, a Markov decision process or a Markov game as a variational inequality problem, your state base becomes infinite dimensional, right? Because you're going to optimize over a function space. So now you're going to run over different challenges of how to actually solve these problems. Just using the projection method is not enough. You have to think about how to actually approximate these functions because you're optimizing over an infinite dimensional space. So a lot of the talks that we're going to hear about today are going to talk about these particular specifics that are associated with different models. But I think this is a high level way of talking about things. And I'm super excited to hear about the talks that from the macro side of things. I'd love to, like, I'm going to ask a lot of questions, but especially what we would love to hear is, you know, what are the specific problems that macro people are dealing with? How can we really bring a computer science aspect to this? So if you want to, like, you know, kind of give your just on things as you're giving your talk, would love to hear about that. And kind of ways to bring into the EC community these questions, as Amy said, which are kind of hard to bring to this community just because maybe we don't know exactly what those problems are and we're not familiar with them. Awesome. So with that, I think I'll pass the baton